So pretty soon, you're going to start encountering questions that are going to tell you some more stuff about friction, okay? And when they start telling you about friction, they're going to tell you something called the coefficient of friction, okay? Now, we haven't talked about friction very much, and I'm just kind of waiting till next week when I have like a full class to tell you more about it, okay? But the coefficient of friction is represented by mu, okay, which is the Greek letter M. All right. The coefficient of friction basically just tells you how sticky the interface between two surfaces would be. All right. So the coefficient of friction between ice and Teflon would be incredibly low because those two things are very slippery. All right. Whereas the coefficient of friction between asphalt and rubber would be very, very high. Okay, so just so you get the idea there. Okay, to calculate friction, and you have this formula on your formula sheet, the force of friction can be calculated by multiplying mu by the normal force. Okay, and normal force is that reactive force between the surface and the object. Okay, everyone kind of follow me there. Right, and we said if we set something like I set my coffee cup on the desk here, okay, gravity pulls the coffee cup into the desk, but the desk pushes back with an equal amount of reactive or normal force, and the cup doesn't move. Everyone okay with that idea? Okay, that's kind of Newton's third law, which again, we're going to talk about next week. All right, so that normal force is on a flat surface at least equal to the force of gravity. Okay, so if I had anything sitting on a surface here, okay, I would have gravity pushing or pulling down, and I would have normal force being equal and pushing up. What if I was pulling this box, instead of that situation, what if I was pulling the box at an angle like this? Would normal force and gravity be equal now? No. Why not? If I'm pulling in this direction, let's say it's 25 degrees above the horizontal, what am I doing a little bit to the box? I'm lifting it just a little bit. And we take advantage of this all the time subconsciously. Okay? If I pull this desk and I pull it like this, okay, there's a fair amount of friction because I'm pulling it horizontally. But if I lift the front of it a little bit, it's way easier. Okay? Because now some of its weight is being loaded by my arms. So not all of its weight is pushing against the floor anymore. Everyone kind of follow? So if all of its weight isn't on the floor, well, then the floor doesn't have to push against it as hard. And as a result, according to that formula, there's less friction. Okay? The opposite is true. If I have the desk like this and I push down on it and try and move it, it's hard. Okay? Because I'm increasing how hard the floor has to push against me. And as a result, I'm getting more friction. Okay? Because I've increased Fn by pushing the desk into the floor harder. Okay? This is why we put sandbags or hay bales in the back of pickup trucks in Alberta in the wintertime. The increased weight in the back increases the amount of normal force, which helps us have more friction over the back wheels. Okay? Everybody follow me there? I know not as many people do that as they used to. They just throw it in all-wheel drive and forget about it. Okay? All right. So let's look at, let's say, a situation like this. I'm going to make up a question here. I want you guys to copy it down and see if you can figure it out. Yeah, I think that'll work. Okay, I want you to calculate the acceleration of this box? No, mu actually doesn't have units. If we look at the formula here where we have FF equals mu times the normal force, when we solve for mu, we're dividing two forces. So the newtons cancel, and it actually has no units. It's a coefficient that describes how big one of these is compared to the other, right? Bless you. Oh, whoops, I left the recording on that whole time. Anyway, okay, so here's what we got to do. Let's put the other forces on this diagram. Let's make this our free body diagram. Okay, what force is pulling down on the box? Gravity. Okay, so we got gravity pulling down. Okay, we have normal force pulling up. Okay, and we have friction pulling backwards. And then I have that angled force out front. Now, that angled force, does it have a vertical and a horizontal component? Yes. Would it be easier for me to find the sum of all forces if I make that, if I find its upward component and horizontal component rather than this 30-degree angle? It's a lot easier to put everything perpendicular on there than to have this angled thing on there. So I'm going to find its horizontal, okay, and vertical component. So I'm going to find, okay, this side by just going cos of 30. So cos of 30 times 200 newtons. All right, so that's 173.205. Newtons, and I'm going to find its vertical component, and I'm going to put that over here. Okay, just so I can keep kind of everything straight. All right, so that'll be the sine of 30 times 200, which is 100 newtons, so I don't even need to punch that in. Okay. All right, that means that I can now get rid of this because I've figured out how much up and how much over it's pulling. Okay, so I can eliminate it, and now my free body diagram's a little easier to look at. Okay, now, are there any other forces on this diagram that I can find right now that I haven't calculated yet? I can figure out the force of gravity. Okay, I have the mass of the box, so I'd have to go m times g. Okay, so 40 times 9.81, okay, is 392.4 newtons. All right. This thing is being dragged along the surface. So is it moving vertically? If it's not moving vertically, what do Fn, Fv, and Fg add up to? 0. Right. Okay? They add up to 0. The box is not accelerating in the vertical direction, so the net force vertically is 0. Does that mean I can figure out what Fn is? Yeah, okay. It's going to be 392.4 minus 100. That way there's 392.4 going up and 392.4 going down. Everyone okay with that idea? All right, so this is then obviously 294, or sorry, 292.4. Okay, now that I have Fn, can I calculate FF? Okay, well, we just looked at that force of friction formula a minute ago. It's mu times the normal force. And I have mu, and now I have normal force, so I should be able to calculate that. So I'll take my 0.150 and multiply by 292.4. All right, so there's 43.86 newtons worth of friction. All right, I'm trying to find the acceleration of this box. I know it's not moving vertically, so I no longer need this number or these numbers. I've already taken them into account. I know they add up to 0, and I got what I needed out of the normal force, which was to help me find the force of friction. Can I now find the net force acting on this object? Okay. Okay, I'm just subtracting because they're opposite. I could add a negative as well. Okay, so 173.205 minus 43.86. Okay, so I've got a net force of 129.345 newtons. Can I now find the acceleration of the object? Yes. Okay, so I can find acceleration by going F net divided by mass. So our 129.345 divided by 40 kilograms. So this thing's accelerating at 3.2 meters per second squared forwards. Okay, that would be about as involved as a Newton's second law question could get. Okay, was there a lot of convoluted reasoning and calculating in that question? Right, I had to find this so I could find that so that I could find this and then that, and then she swallowed a spider to catch the fly, and I don't know why. Right, like there's just so much there that you have to do to get to the end. So I mean, this is not an unreasonable problem for you to expect to get near the end of the unit, okay? But it does involve you really having to see all the relationships in a question. Because this isn't an inclined plane, right? It was on a level surface. I was pulling it at an angle, but it wasn't on a plane. Yeah, so that's a good question, but yeah. And unfortunately, a lot of people do make that mistake on a test or a quiz. They're like, oh, I see an angle, it must be an inclined plane. Well, it would say in the question, pulled along a level surface. As soon as you see level, okay, F parallels out. Question? No? All right. Now, speaking of inclined planes, I'm going to make up a quick inclined plane question that I want you to try before we head over to math. Okay? Yep. Okay, calculate the acceleration of that box. All right, so we got 140 newtons that are pulling up the ramp. Okay, we got friction pulling down the ramp with 30 newtons. What else pulls down the ramp with some force? Well, the component of gravity, which is, what do we call this force? F parallel. Okay, so we've got to figure out F parallel using that internal triangle that's always the same, right? So the force of gravity on this one is 196.2 newtons. Okay, and then this force here is the normal force, which I'm not going to need in this question. And this side is F parallel. This side here is 30, or this angle, sorry, is 30 degrees. Okay, so F parallel is 98.1 newtons, because the sine of 30 time is 1/2, right? So a half of 196.2 is 98.1. All right, now I can do the sum of all forces. Okay, so I'm going to have 100, come on, turn on. 140 minus 98.1 minus 30. All right, so we only have 11.9 newtons worth of force going up the ramp. We divide that by the mass of our box, 20 kilograms. We're looking at 0.60 meters per second squared up the ramp. Okay? All right, let's head on over.